wave your hand or something. It's a pleasure to be here and share with you some of the experiences I got to be involved in while I worked at TDOT, and got to see a lot of different type of geo-hazard situations, from landslides and sinkholes and caves, and all the way to discovering a brand new fossil deposit up in Johnson City. It's now called the Great Fossil Site. Never in my life did I ever think I would be involved in something like that and get paid for it. But it's been great. Well, I want to share with you some information and how we dealt with Karst at TDOT, mainly in East Tennessee. Most of my information is going to be about East Tennessee. But this is there's all kinds of Karst maps floating around. This is a version that was developed when TDOT and the Federal Highway Administration had a Karst runoff drainage project, research project, and P.E. Lamoureux and Associates was our contractor who helped do this. And anyway, this is a map. Here's Tennessee. You can see we've got a large amount of karst. Here's the Florida karst, the Edwards Aquifer karst down in Texas. A lot of this karst is actually evaporite deposits, salt. Been out in eastern New Mexico. You've seen they've had some huge collapse issues with the evaporite and the oil drilling aspect of it. This is the Missouri karst, and this is the Ridge and Valley karst here. Anyway, here is a map that we developed through this study showing areas of intense sinkhole activity, with the red being greater than 10% sinkholes, and the green less than 1% sinkholes. It's all carbonate, obviously, and you can see how it's scattered. This would be Sequatchie Valley right here. Here's that western escarpment of the Cumberland Plateau. It's really a cavernous place up there. Closer, you can see here's Knox County and some of the more well-known karst areas. Well, what does some of this karst look like? We have lots of caves. This is one of the large ones. This is the Evelyn Cave down in Roane County. Some of the caves are very large. A lot of them have streams in them. A lot of them have secondary deposition of calcite in the form of stalactites and stalagmites. And these caves can be quite beautiful. The caves also contain wildlife, this is a typical cave salamander. I think it's called the Tennessee cave salamander, I believe. And we also have the bats. This is the eastern pipistrelle. Need to go higher? Okay, let's start. So we have the karst, and from a geotechnical engineering aspect or standpoint, we're looking at the karst geohazard. What, how is this going to impact our highway? And our concern is safety for the general public. And with respect to that, our interest is in sinkhole collapse. And most of our collapses that we deal with occur sort of like this. We have lots of residual clays that develop over the carbonate rocks, mostly limestone, some dolostones. And this drawing depicts the East Tennessee structural version where the beds are tilted, so we get this highly pinnacleized soil rock interface, where some of you are involved in drilling for foundations for buildings and all. This is why when you can drill 10 feet and hit solid limestone and move over 10 feet, and you might go 30 more feet before you hit limestone again. And it's very irregular. in this setting where you have surface water infiltrating the soil is gradually eroded into the openings in the bedrock and flushed through the system. And when that happens, you get small voids to develop in that soil. And these voids get larger through time. They'll get larger and larger, and you'll see at the surface you may get some subsidence. And then the voids get so large and the residual soil cap is so thin that it can't hold itself up. It loses its shear strength. And then it ends up looking like this in a collapse. And in real life, this is what it would look like. Very pinnacleized, we call karstified bedrock. Again, our problem in TDOT is safety. We want to look at this from a safety standpoint. So this is what we have to deal with. See this young man? Guess who that was, or is? That was me about 35 years ago. And we have to deal with these sinkholes that develop in our ditch lines and in the roadway. Some of them are quite catastrophic, and some of them aren't. But in karst areas, this is what you have to deal with. This can ruin your sleep pattern very, very easily. You can see a number of different situations. Most of our sinkhole collapses along the highways. I was telling Jennifer earlier, I did a study on our records that I had kept. 73% of the collapses occur in ditch lines. And of those 73%, 93% occur in unlined ditch lines. It's real critical. Remember that. It means there's nothing keeping the surface water from infiltrating down. Here's a couple of guys looking for the bottom. And these can occur away from the highway too. This is a house up in Morristown. Some of you may have seen this in some of my publications. This is in Morristown, which is in a well-known karst area. And subdivisions are built in the karst area as well. And this fella lost his septic tank, which used to sit right here. And here's his part of his drain field, and this is the line coming. There was no sewage system developed for this subdivision, and so this guy lost his house because there was no room to put a new drain field in. But they can occur away from the highways. Sinkhole flooding is another issue that we deal with. And, if you build a highway or road through a sinkhole, at some time you need to expect it to flood, because it will. This is in Knoxville. This is Prosser Road. This guy tried to make it across. Obviously he didn't. And the other issue is groundwater contamination. I think most of y'all are involved in that. And this is one reason why it can be such an issue. It used to be a very common practice. I think the education that is being done publicly about karst and caves and groundwater is helping this situation, but this still exists. This right here. All right. To help us develop highways, particularly in karst areas, we have to map where the karst is. And I'm going to show you a series of maps and projects where we were able to go out and map sinkhole locations to help to aid us in developing the EIS for certain projects. and some of these you will know, you'll know about. They'll be familiar to you. This is the first one that I was involved with was back in the early 80s when we were planning for the extension of the Mississippi Parkway. And we got to go out and do our geotechnical aspect for the EIS. And these were the routes that were given to us to study. We were going from this point on I-40 to this point on US 129 out near the airport. And we had to look at all these routes. So we went out and tried to map everything. This is, I thought I threw this in, some of you may be interested. This is the Cedar Bluff interchange. When it was first built, I think this shot was made in 59, I believe, or 60. It's amazing, isn't it? Do you see anything that you actually recognize in that picture? This is the same area in the mid 80s. Here's the interchange right here, I-40, and 10 Mile Creek drains this whole system, surface drainage. I don't have a current day picture. I wish I did. I'd like to see it. But, this is where 10 Mile Creek goes underground. This is the 10 Mile Creek Ponor that Sid or Hank mentioned the term Ponor. This is the 10 Mile Creek Ponor. It goes underground. And a series of cave openings have developed there. The 10 Mile Creek cave system. This is one of the entrances here. And this is the Keller Bend Bluff area, which one of the alignments went across, and there's a number of caves located there. This is what we ended up with as a Karst map. It shows numerous areas of numerous caves and sinkholes in the red, and in the yellow we expanded that to include the negative drainage basin for the Karst area. As everything that drains, surface drainage here flows into the cave system. It's all negative. It's not a positive draining system. And I believe this particular system here is over 15 square miles. So that's a big surface drainage basin that goes into the subsurface. It's very large. Well, after we looked at it, our recommendation to the department was to follow this route and then cross over along this boundary and then come on across Tools Bend right here. And as you may know, here's the route that we recommended from a geologic standpoint, and that's the route that we got to go with. There were other factors that entered in, including right-of-way cost, relocations that had to occur. At that time, I don't think environmental considerations were weighed all that heavy. Today they would be, but back in the 80s, they considered it, but it wasn't a real heavy factor. But thank goodness this was the route that that was chosen and the one that was built. So that's a type of Karst map that we make, and y'all can make it too. This one, probably a lot of you know about. This is what was known as the orange route of the Knoxville bypass. And it's been studied to death. And I'm going to share with you some of the aspects of it. This route was to bypass Knoxville. Was to bypass Knoxville from the I-40-75 split to just southwest of Knoxville, and to connect back to I-75 north of Knoxville, up close to the Clinton-Norris interchange. So we have about 23 miles across country that we had to study, and we became involved in the EIS aspect of it. So in order to do a proper evaluation, we had to map all the sinkholes and the cave systems there, as well as springs. So here is a topo, here's a number of topo maps put together showing the proposed alignment or the corridor that was to be studied. This area here, I believe, is where the route crossed Pellissippi Parkway, the existing Pellissippi Parkway. So that give you some idea. So we went out and we located sinkholes using the 20-foot contour interval topographic map, 7.5 minute quads. Now there's a big caveat here that I'm going to tell you about at the very end of the talk. Okay? These are great tools, but don't hang your hat on them. All right? So we had a 1,000-foot wide corridor that we had to study, and it wasn't just geotechnical, it was also environmental. We worked hand in hand with some of the environmental aspects of it. We found 63 sinkholes within the corridor and 225 either within or right adjacent to the corridor. And I'll show you what some of these look like. Some of them are very active, and some that the cows didn't seem to mind very much. This is in the Hardin Valley area. Some of you are familiar with Hardin Valley. A lot of karst in there. These are just some of the cave entrances and springs and ponors that we found during our investigation, and it was quite an ordeal. Here's some sinkholes. You can see these are close to 150 feet in diameter. There's one here, one here, one here, then another one right here. So these can get very large. And the thicker the residual clay soils, the larger your sinkholes can be. That kind of relationship there. In mapping out these sinkhole locations, what we wanted to do is map where the sinkholes were, where we already had sinkholes, where new ones were forming, to get a feel for it. And also located caves, and some of these caves we actually mapped and tied into our survey grid so that we would know spatially where this cave was with respect to the center line of our road and the resulting design of the road. Well, if there was going to be a cut slope, was that cut slope going to intersect where the cave was? So we did some pretty extensive surveying in a couple of these caves. And I'm going to show you one. This is Spring Hill Saltpeter that was within the area. Here is the entrance room. You can see how big. Here's a person standing here. It's a very large volume of cave. And here's the entrance in a large sinkhole, existing sinkhole. And we did our mapping, exploring. We actually did a major bat survey here. We hired professionals to come do this. We found there's 7 different species of bats that were using this cave. It's pretty amazing. I figured it'd be pipistrelles and big browns and little browns, but there were others that were using this cave. And I threw this in, this picture here. Y'all see a face or a head in that? Looks like the Indian head nickel, doesn't it? I didn't even know that existed. And I made the photograph when we were there one day doing some mapping and I made this photograph, and I got back to the office and started looking at it, and whoa, this head popped out. And it made me think, Native Americans used this cave. And there have been archaeological surveys done, and they have found some things. I'll show you here in just a second. But it made me think, did the Native Americans get this same view at one time and make them think that this was a spiritual, special place for them? I just wonder. It's sort of interesting. I also found some of these glyphs in Spring Hill Saltpeter. These are actually charcoal, and charcoal was dated. I think these were somewhere around 1,000 years old, I believe, that they found. So this cave is very significant, and So we were going to take extreme measures to not impact this cave if the project went forward. This is one cave. We made a map of it, like I said, and this is here's a plan view map, but we also did a profile and connected it to our survey so that we would know exactly where this cave was located in reference to the highway. Another cave was Cherokee Caverns. It's a well-known, formerly a commercial cave that was adjacent to the corridor, and has been re-nurtured, I guess, in the last 20 years or so by some by the caving community. And it's used for educational purposes. It's a real good place. They've done a real good job, and there's some unusual formations there. And we made a map of that one as well. I don't know, does it show up very well? Can y'all see this? See the map? I don't know how well that's showing up. But we also did a LiDAR survey of this cave. There, can you see it okay there? The entrance being down here, and this is the entrance. We did a LiDAR survey where we had planned to, if the project went forward and we were going to build the project, after the project was completed, we could go back and do another LiDAR, and the software would be able to tell us if anything had changed in the cave with regard possibly to our impact. I mean, the LiDAR survey is extremely detailed. In 5 minutes, the survey instrument will gain several million survey points, all digitally located. It's almost like a photograph. It's amazing, but it's really good technology. Now, as a result of this, our bridge inspection people are using the LiDAR to survey bridges now and compare the surveys using the LiDAR to see if new cracks have developed that they hadn't seen. It's pretty good. It's real good technology. So we mapped this, and here's a visualization that we did. This was in preparation if we went to fruition with the project. This is looking kind of east-northeast. This is Oak Ridge Highway here. Here's a railroad here, and there's a large stream that comes through here somewhere. Maybe it's over here. And we superimposed this with the proposed route. It's a bridge over the highway and the railroad. These are embankments. These are probably 70 feet high. And if you look on out the bridge, there's a cut slope here and a cut slope here. So it's sort of a visualization. But we were able to, because of our survey, we were able to locate Cherokee Caverns with reference to our project, which I thought was a pretty slick thing to do. And one other cave I want to talk about before I show you the Karst map that we developed. This is called Ghost Cave, and I'm not going to tell you where it's located. But as a result, we found a very significant population of gray bats. And the grays are on the endangered list. And this particular population is a maternity colony, meaning that the bats come here at a certain time of the year and raise their young. They give birth to their young, raise them, and then probably in the fall, September or so, they all leave to go to a hibernaculum, someplace that they hibernate. And these are some of the bats. The estimates were close to 5,000 in this colony. Now, this is not a big colony, but nevertheless, it was significant enough, and it was within our corridor that we had to study. So we made documentation of that. Let me go to the next slide. Again, 63 sinkholes within the corridor, 225 total. We located 25 caves within the survey, or within the corridor. And this is the Karst map that we developed from our study. It was like we were trying to connect the dots with the highway with all the karst areas. I mean, you know, we ran out of it here, so we went over here and went up this way, but we had to get to this point, and you know, as you can see, structurally, you can see these are long, linear, northeast, southwest trending belts of karst, of sinkholes. And that's because of the geology, underlying geology, the Ridge and Valley type geology that we have. So this was a karst map that we did. Real quickly on these two, this is a karst map that we developed for the area. This is Kingsport, Blountville, and Bluff City, and Bristol Motor Speedway is sitting right here. And they were trying to get a good route for traffic into this area, as you can imagine. You imagine why. So they gave us these corridors to study. So we went out and mapped areas of intense sinkhole formation and caves. These were numerous cave locations here, and then the yellow were intense sinkhole formation. And these were some of the sinkholes that were located there. Some of the places, the landscape is very gentle, and to an untrained eye, you wouldn't think that there was a problem, but there is. Another area up there in Elizabethton was the Elizabethton bypass, and we did the same thing there. We were looking at this blue route, series of routes, and then this green, there's a series of green routes. And this was to be the Elizabethton bypass. The blue areas are numerous sinkholes, areas of numerous sinkholes that we mapped. The red areas of numerous caves. This blue route was not a good route, and we recommended not using that route to move over here. As it turns out, the green route was perfect geotechnically, but archaeologically there were numerous burial sites all along this stream over here. So I think right now the project's somewhat dead, which happens a lot of times. The more information you get. These are some of the sinkholes on that route. Here's a guy got his outhouse right in the middle of it. I hope he doesn't have a well nearby. Here's another one. Some of these are very pronounced. This one is the South Knoxville Boulevard extension, State Route 71. Some of you may be familiar, some not, but this was a real interesting project. Here is downtown Knoxville, and the existing James Watt Parkway, State Route 71, ends right here, crosses the river just north of, or just east of town, and ends in this location right here. This is Chapman Highway, which used to be the main route to the Smokies. This is where the Tennessee River starts. This is a French Broad, this is the Holston, and they connect right here, and then it forms the Tennessee River. So we had this big corridor area that we wanted to study, and we were trying to go from that point to this point. So most of the thinking was we need to stay on this side of Chapman Highway to cut down on the number of crossings over Chapman Highway that we'd have to build. So we went out and did surface mapping of karst. So we started with the topo maps. Again, it's a good place to start, but don't hang your hat on it. And I'll show you here in just a minute. We went out and field checked these and located a lot that weren't on the topo maps. And these are just some of the features that we found. Sinkholes with cave openings in them. Here's a spring. uh, very low relief topography, but they were sinkholes. Here's some more, some relatively recent activity here and here and right here. So we did the sinkhole location study, mapped it out, and here's this shows the corridor boundary. Here's Chapman Highway, and this is where here's the parkway, and it stops dead right here, and we're trying to get over here. So you can see we've got a lot of karst in here. I don't know whether you can see the pattern right here, but the next picture will show you. This was the karst map that we developed, the blue being the numerous areas of numerous sinkholes. And you see this peculiar shape here. This was really odd, and it stuck out. I said, I know there's a structural reason why this is like this. And here's a geologic map, those who are geologists. If you'll look closely, you'll see this is the host formation. It comes down and it swings back around. This is the Lenore, and then this is the Knox. And actually what we have here, or have, is a plunging anticline where the rocks have been folded, but the structure itself is dipping down into the southwest. Here's the axis of the structure, and this is the dip direction of the structure. So if we go back, you can see how this is shaped. So it's shaped because of this structure pattern. Geologically, it's a real interesting thing. Most people would just shrug at it and go on, but if you're a geologist, it's sort of interesting. This is called the Rocky Valley Anticline. In doing the study, we found some sinkholes that were real suspiciously located. There's a park there called Imes Nature Park. And this is where it's located. Here's the headquarters are right here. And this is the Tennessee River. And this was an old quarry. It began as a marble quarry, and it ended up just being a crushed stone quarry. Some of the earlier previous marble quarries are represented by these gashes in the landscape right here. What we found out through the caving community was that, there was a biologist at UT who was doing a dissertation on the buried cave salamander. And we got connected through TWRA and found that the buried cave salamander does exist in this cave system called the Meach Quarry Cave System. Runs through here. And they suspected that there would be some sinkholes some distance away that might be recharge point for this stream. There's a perennial stream in this cave, runs all the time. So it must have a very large basin, groundwater basin. But the salamanders live off of detritus that is flushed into the system from these sinkholes. That was the suspicion. So we thought, this was very significant because the buried cave salamander is an endangered species. It will be if a project is ever built. It's funny how they list things, but that's what we were told anyway. So we decided we better find out for sure whether these sinkholes are connected to this cave system, because we certainly don't want to purposefully go in and impact this endangered species. So we set out on a project to map this cave as far as we could, and then do some dye tracing to see if they're connected. Here's some of the old marble quarry workings. This is where the stream in the cave comes out, and it fills up this old quarry pit with water. So this runs 24/7, 365. Sometimes a lot more volume, sometimes not. Here's the surface. Here's an aerial shot. This is where the water comes out of the cave system, and these are pits. And there's openings into this cave system at these different places. And this is the one furthest upstream in the cave itself. And that's where we started our survey. And this is the entrance that we went in and started our survey. And again, our survey is connected to the engineering survey for the proposed road, so that we'd know exactly where this cave is located. And I mean, you may not think it, but the roadway surveys, they're very, very accurate. And over the last 10 years, they've become extremely accurate as to where they are spatially with the new GIS and using the satellites. So we put in benchmarks out here that we got our bearings off of to go into the cave. And we surveyed about 3/4 of a mile in the cave. And it was not pleasant. We had to stay in water that was, in the 50s degree range for 4 to 5 hours at a time, and it'll work on you after a while. It was also dangerous in that it was very slippery. There's lots of mud, and of course these salamanders lived in here, and we had to watch out for them. This is very typical of, this is yours truly. This is very typical of the caves formed in the Holston Formation. It was an old Ordovician bryozoan reef structure. That's real high percent of calcium carbonate, 98, 99% calcium carbonate. It's pretty pure. These are some of the formations that we found in there. And a lot of these white formations, very interesting. This is the fella right here. This is the buried cave salamander, and what we found from Matthew Niemiller, who was the PhD student who was studying these, he had found 16 individuals in this cave, more than any place else in the world. This cave has the largest population of these critters. So we definitely didn't want to do anything to hurt them. We made our map. Here's the map with photographs showing where some of these things were. And in a goodwill gesture, we gave this to the Imes Nature Park so that they would have it for their records. Some more pictures of the cave, and again, a last shot of the karst area. Right now, the project has been killed. It's not. Right now, it's dead. You know politicians as well as I do. Somebody can rejuvenate this thing, but we've got a lot of good information on it. And here's something that we were able to do with this project. We located through GIS every karst feature that we found. And not just karst, but springs, churches, cemeteries, parks. Everything was located in GIS, dumped into a computer, and the consultant, which I think was Palmer, I think it's Palmer Engineering, had a software program called Quantum. I think it's developed in Australia, where it takes all of these constraints and chews them up, and it spits out roadway corridors that tries to miss all the constraints. And this is what it came up with. As you can see here, the sinkhole area that we were real concerned about is right here. These sinkholes right here, because they feed this system. This is Imes Nature Center, and this is where the Meads Quarry Cave is located. But these are all of these are sinkholes, and the cave openings were also located. So it spit this out. It looks like, one of the preferred routes is this orange route. It gets real close to this park area, but there's different routes that could be chosen. The terminus was going to be somewhere along Governor John Spear Highway and Chapman Highway, that intersection. But again, this is a dead project, so who knows? But we did get a lot of good karst information from this survey. Now, I'm going to close with this little project. The department was proposing a welcome center site on I-26 up in Kingsport. And I think the site was about 25 acres in size, but the study area is about 300 acres. So we pulled out the 7.5 minute topo maps, 20-foot contour in. This is key. You can see, yeah, we've got some sinkholes in here. If you count, you might count 30 some odd sinkholes in this area. We requested a 1 meter contour interval map, flight map, and we got it. And this is what it told us right here. Yeah, there's a whole lot more sinkholes there than what the map showed. So don't hang your hat on a topographic map that has a 20-foot contour in it, because you're going to miss a whole lot. And that's why it's so important to go out and field check where your study area is, because there may be things there that are not showing up on the topo maps. So just for your information, there was around 197 sinkholes here. And this is an example of one of the sinkholes. Just my good friend Eddie Sutton, Sid, you might know him. Here's what some of them look like. We found 7 cave entrances here. Never wanted to put a big visitor center here. What we were able to do is get the site moved to the south about a half a mile or so. It got out of this karst area, across a boundary, a geologic boundary, and so we were able to stay out of that. It was not a real good situation when I announced to the department that we can't build anything here. This would be crazy. And they asked, well, what can we use this for? And I said, it'd be a great place for a karst park. So I don't know what would ever become of that. But anyway, I'll close with a shot of some China karst. This is some of that haystack tower karst that you hear so much about in China. And I got to visit there about 10 years ago and see this. And it's quite amazing. This is water buffalo here, but these towers are 1,500 feet high. They're full of caves. It's amazing to see. They have a great resource. There's about 4,000 square miles of this in China. It's just an amazing area. And they're not real sure they want to develop it, and I hope they don't. But they're looking at building highways around this place. Anyway, that's all I have.